Hi, I'm going to present this paper once for all. Train one network and specialize for efficient deployment. This is a research by MIT and MIT IBM Watson ALL. So for the population, there are growth in model sizes and computation cost in these days. So models, for the accuracy, models are getting bigger and have to execute with the large model size and also with the computational cost. However, there are various types of hardware resources, and some of them does not have as good as like server does. So and also through their engine memory and also computational capacity, by considering them, optimal neural network architectures can be vary significantly. To solve that problem, the domain allocation methods are proposed, but there are some limitations for the previous methods. So usually, experts design compact models by compressing existing models to specialize in certain hardware platforms. However, designing specialized DNNs for every scenario is very expensive. Even human expert doing that is very expensive, and also utilizing NAS, neural architecture search, machine learning version, is also very expensive in terms of cost of energy consumptions and also computational cost. Yeah, so there's some related works like this big three, efficient deep learning and neural architecture search and neural network. So efficient deep learning, as we know well, there are some neural models like SqueezeNet and MobileNets, and also there are some methods that we can use like network pruning and quantizations. And for the neural architecture search, as I briefly mentioned in previous slide, we need to there are some limitation related to the cost. So we need to repeat the search and training for new hardware platforms, so that it's not scalable to various types of hardware. And also, each trained models does not share weights with other models. So if we want to deploy several variants of the models into one mobile device and use some of them by considering the trade-off between the computational cost and the latency, in that case, we need to download and use that model, different kinds of models in the memory, and they takes lots of spaces because they do not share the weight. And for the dynamic neural networks, they does provide degree of flexibility, considering they provide channel pruning. However, they inherit a pre-designed neural network, and that might not be the optimal neural network for the new scenarios like hardware platforms. So the key idea these authors propose is a once-for-all network. So basically, it is a network that is trained once and can be deployed under diverse configurations. The inference is performed by selecting only part of the networks, the sub-networks, so the cost can be reduced a lot. So in the left figure, you can see that after training once for a network, we can adapt that network to the various hardware platforms or hardware scenarios like cloud AI, mobile AI, and tiny AI. And on the right figure, you can see because it takes only it takes only constant time to architecture search for different platforms, so the design cost reduced a lot. So the previous method is linear to the number of design hardware platform scenarios. So the major challenge is training the OFA network is not an tedious job. It has a complex problem it requires a joint optimization of the weights for the lots of combinations of subnetworks. By simple mathematics, the author provides that there is 10 to the power of 19 combinations of available subnetworks. So enumerating all those subnetworks for the training is very computationally prohibited, so almost impossible. And randomly sampling some of the subnetworks will lead to accuracy drops because not all of them are trained, and also like different subnetworks are interfering with each other because they share the weights. So the key solution is progressive shrinking algorithm. They train the largest neural network first and then fine-tune the smaller subnetworks. By utilizing the weights of the larger networks, it initializes better by selecting important weights of the larger subnetworks. So the subnetworks training is facilitated, and also it achieves better accuracies. This is kind of a generalized network pruning method because it shrinks in the terms of not only in channel or width, and also corner size, and also depth, layer, and also resolution. This is the key result. So comparing to other CNN methods, the OFA on the left top side achieves very good accuracy and also with very little computational cost. So from this on, I'm going to explain details of the how to train the model, etc. And this is the problem formulation. And actually, like this is the only equation appears in the paper. Okay, so there is a C. I guess there's no explanation of what is C, but I guess that is the truth. So they select the part of the model. The whole model is the WO, and there's an architecture configuration, ArcI. So for each architecture configuration, they select the subnetworks of the WO to minimize the L value. Actually, L value is also not defined in the paper, but I guess that is, yes, somehow related to accuracy or like other energy consumptions or something like those constraints. So they can pick the WO, which minimized the subnetworks like loss term for every architecture configurations. And the major contribution progressive shrinking is executed in this order. So elastic resolution is resolution shrinking is done first, and then corner size, depth, and then width. So the comparison to network pruning is I mentioned in previous slides, but the network pruning does shrink for the only width axis, but progressive shrinking does that in the 4 dimensions, like depth and corner size and resolution. And also network pruning, they fine-tune the small network only, but progressive shrinking, they fine-tune the both sides, large and the small networks. So for the elastic corner size training, the 7x7 network is first trained, and then the center 5 times 5 corner is trained using the previous 7x7 corner. And then 3x3 is the center from the 5x5. But those weights are not directly used again, and they use the transform matrix between the between each of them two pairs. And those computational costs for the transform matrix is very negligible. Yes. And for the elastic depth, at most they use the 4 layers, and they also have 2 or 3 using like options of using 2 or 3 layers. And if they use the 3 layers, they just use the first 3 layers and skip the last layer. And for 2 layers, they use the first 2 and then skip the rest. And for the elastic width, there is like 3 options of using 3, 4, 6 channels. And first in the figure, there is only 4, but they train the 6 channels. and like sort them in the importance and pick the 4 in this slide, in this figure. Like they pick the 3 top and use them for the like sharing 3 channel models. And then also pick the top 2 importance channel for the less, like smaller subnetworks. So this was the training phase of the OFA, and then this is the model deployment part. So they need to drive the specialized subnetworks for a given deployment scenario. So search for a neural network, this is the search part, satisfies the constraints of the target hardware while optimizing the accuracy. To achieve these goals, they use the neural network twins to predict the latency and accuracy given the neural network architecture. Like without executing them all the time, they need to adapt to hardware like scenarios. They use the predictor model to get the predicted latency and also accuracy. And this is the evaluation result. First is shows that the effect of progressive shrinking. So orange is without progressive shrinking and green is with the progressive shrinking. DWK is depth and width, the channel and corner size. So for these subnetworks, there are actually 5 units of those configurable units of like depth, width, and corner size, and they were they fixed those 3 configuration for those 5 units, and then they trained it. And so with the PS, they utilized the weight from the larger subnetworks. So by using those knowledge, they achieved like 2.5 to 3.7 increase of the performance. And when it is compared to the previous NAS models, this is executed on Pixel 1. So when you see the green box, you can find out they achieve good accuracies compared to other NAS methods. And on the blue box, you can see that the search cost is very low compared to others. However, the training cost is quite high compared to other NAS models. But usually, like other NAS models, they are linear to the hardware scenarios. In this case, that is defined as N. So as N grows up, other NAS model like goes very quickly, but the OFA, like some of them stays constant and some of them gets like slower or really bigger. And yeah. So this is the evaluation results, and there's a computational resource constraints. So with the computational cost, with the same computational cost, they achieve 2.8 higher accuracy, and with less computational cost, they almost get the similar accuracy results. Yeah, they also check that it works well in Pixel 1, like this restricted resource constraint scenario. And also they check the similar evaluation on like 6 types of various hardwares. And also they check the result from like server side and also FPGA scenarios. And they also check that it works much better compared to other NAS methods. And OFA chop 25 means that after they pick the OFA model from, like after they select the optimal OFA model from the like subnetworks as a subnetwork, they trained like 25 epochs more training. And when they consider the FPGA scenario, there is some like bottleneck related to memory usage. So if they use more arithmetic, like more computational operations than the memory usage, then they can get some more benefits from like those strategies. So they show that their model can adapt in a way that can utilize the arithmetic intensity. So as a result, they showed better like computational capacity on the right two figures. And from these slides, they shows how their model can configure differently the intermediate like layers, and also how they use the different like parameters. So conclusion, OFA is an serverless like decomposed model training from architecture search. And also you can deploy to like various number of hardware platforms. And they propose the progressive shrinking algorithm to enable training the subnetworks, which is needed for OFA to learn. So for the critique, it achieves great performances, which achieving on user tolerable performance. And also like challenge to solution connection was quite clear. So they executed exhaustive experiments on a diverse range of hardware platforms and also constraints. More weaknesses, only one equation was presented, and no other mathematical or algorithmic descriptions were provided. And also, LBEL was not defined, like some of the equation was not fully explained. And also, like they utilize some other techniques like knowledge distillation and also evolutionary search, but they do not mention why and how they use those methods. And some other details. Yeah. Unfortunately, it was not, easy for me to get a new idea, formulate a new idea. So I'll skip this part. Thanks.